So the first presentation, and this is a session on airframe noise, and again it looks like Yulu has given the title, Shock Formation in a Non-Uniform Gas Dynamic Flows. This is by Professor Sujith of Indian Institute of Technology from Chennai, India.
Thank you very much. It's an honor to be here on this great occasion. Can I get a mic? Yeah. It's an honor to be here at this great occasion, and I'm going to talk about shock formation in non-uniform gas dynamics flows. And I see that most of the talks here are on sound generation. For a change, I'm going to talk about propagation. I guess at least one person should start about what happens to sound once it's all generated. I guess that's the reason I got it here. And before I start, I want to acknowledge my student co-author, Manu Tyagi. Aeroacoustics is the generation of sound by flow hydrodynamics. But if the flow domain is large, and there are problems in which you are interested in what happens in large domains, a sound generator will propagate in the flow. And if there is a flow, it can interact with the flow. Example of that would be like CD nozzle or something, or in a sonic boom where sound propagates over a very large distance. And nonlinearity becomes important if the sound propagation is happening at high amplitudes and high frequencies. And my introduction to this phenomena was somewhat circumstantial. Day on at my graduate school, I learned that you have to hit the ground running, and I was given these microphones, and I learned that they are awfully expensive, much more than my stipend. And the day two, I measured these things. I thought, okay, I didn't know much about acoustics, and I thought they looked like sine waves, but I got some things which were quite far from sine waves. And I thought, oh my God, all my assistantship is going to be taken by my professor to replace these microphones. But then I eventually learned that this was really okay, and this was called nonlinear distortion. But was too busy in graduate school to do anything with it, so now I'm away from graduate school. And so eventually, some 15, 20 years later, I'm revisiting the problem. So we all know from classical papers that a plane compressive disturbance traveling in a quiescent flow will steepen and form a shock. Plane expansive disturbance would relax. However, there can be non-uniformity in the flow, and this can make the process complex. And so there is this combination of nonlinearity and non-uniformity, and this can make the subject complicated. So the goals here are to study analytically the nonlinear wave propagation in a general non-uniform flow, and when and where can a compression wave steepen to form into shock? That's one question I want to ask. And would an expansive disturbance always relax, or would it reach some other state like attaining a permanent form and so on and so forth? Let's just quickly list some of the applications. Got into it because of the rocket nozzles and flow in CD nozzles. The other interesting examples where you have large gas transport systems where you have pipelines carrying gas over kilometers, and you have sometimes oscillation set up because of the valves being closed and open and so on. And these systems pipelines are maintained at very high pressures, and so you can actually get high amplitudes, and this can propagate down and could become shock because there's kilometers of pipeline. And there is, of course, unsteady flow in engine exhaust and combustors, and you can look at transition from deflagration to detonation. Of course, there's this sonic boom which aeroacoustic people are very interested about. So this is indeed a well-posed problem, and someone was saying that Fox Williams likes well-posed problems. But I didn't do the well-posing. It was by Whittam and people like Whittam and Crichton, so they well-posed the problem. And only Euler equation, and this is like a generalized Euler equation where you can think about changes in area and changes in, or some other inhomogeneities in it. You can write it in a it's a hyperbolic system, and you can write this equation in this generalized form where ui is a flow variable, aij could be in general a function of uj, and vi is a function of uj and x. And we all know from classical fluid mechanics that determinant of aij minus c times delta ij would give the characteristic velocities, which would be u plus au minus a and u in a classical fluid mechanics sense. And BI could represent things like effect of duct area variation on continuity equation, or non-uniform Mach number, or frictional term in momentum equation, or sometimes you have heat addition in the energy equation, and so on. So now VTAM and Crichton, they have worked on this problem, but they have done the problem when they had a quiescent or a uniform flow downstream of the wave, which will actually make ui equal to constant, and vi, which is a function of ui, is equal to 0. So then the equation can be solved quite nicely and elegantly, and it is there in some of the papers by VTAM in 1950s, and there in his textbook, really elegant stuff. But things get messy when vi has to be taken into account when ui is there. Just some more definitions so that I can explain my talk better. I call a base flow as a given steady flow, and in the present work, base flow is the steady state solution of the governing equation. So just the unsteady term disappears, and that's the base flow. Disturbance is at any point in the base flow, if I perturb the flow variable, that's disturbance. Wave front is the leading edge of the wave, and slope is the first derivative of the flow variable at the wave front. So if I have a general flow where I have a base flow whose slope is like this, and then I perturb the slope, first derivative, a little bit, and this is how a compression wave would look if I'm looking at a right-running wave, and the expansion wave for a right-running wave would look opposite. It's coming down. So this is just a schematic representation. So the methodology I'm using is VTAM's wavefront expansion. So if I have look at the trajectory of the wave as x equal to x of t. Now x dot of t, which is the first derivative of the characteristic velocity, and what we want to do is to sit on the wave and travel with the wave and then look around. So if we write variable x minus capital X of t, which is the distance behind the wave, distance from the wavefront, and we can expand all the flow variables uj in terms of base flow plus first derivative plus second derivative. So this eta squared here, I missed it. So this is like a Taylor series here, and uj naught is a solution of the steady flow equation, which is this. The unsteady term is here is missing. uj1 is the first derivative of the flow variable, uj2 is the second derivative of the flow variable, and so on and so forth. So there's a way to look at the derivatives. And now, similarly, we can expand these terms in the equation aij, this tensor, and bi in terms of the distance zeta from the wavefront. And then what we do is to look at the coefficients of eta power 0 and zeta power 1, and then you can write these equations for this. So if you write this in expanded form, these equations can take a long line, but long lines, but right in tensor form they become sleek and elegant. Now, terms in square bracket means they're evaluated at the wavefront. So we have these equations like that we can write for zeta power 2 and zeta power 3 and so on and so forth. And the question is how to solve for the derivatives. Now, change the ui, which is a row vector, into a column vector, and you can get this equation 5. Now, don't worry, it's not very complicated equations. Most of the terms will eventually cancel out, and it's a happy ending. So if you take the left eigenvector of Li of this system, aij minus x dot t delta ij is equal to 0, that should be, this whole thing should vanish, which would mean that I can back out this term completely, and I can get this sleek equation. So that's the reason I multiply by left eigenvector. So therefore, here we can eliminate the first derivative and get the zeroth derivative, or the this is a relation for the steady base flow. In fact, this will actually give the things which are given in the standard gas dynamic textbook, the base flow equations of 1D gas dynamics from the full equation. That's the leading order term. And then similarly, we will try to eliminate the u2. So again, change ui2 into a column vector, and then multiply by li, which is the left eigenvector, and you can eliminate the second derivative, and you get this equation. Now, what we need to do is we have to look at the disturbance. So we have a base flow which has a slope, certain slope. And why are we interested in the slope? Because when the slope goes to infinity, your wave is bigger because you have infinite jump in the flow variables. So we look at some quantity sigma, which is the difference between the new slope and the base flow slope. Okay. So uj1 equal to uj0 plus sigma. So this is sigma is nothing but the difference between the perturbed slope and the slope of the base flow. If there were no base flow, it's just the disturbance. So now, if you put this into this equation, you get a big messy equation which has the second line is full of inhomogeneous terms, which makes this equation, which is actually a required equation, unsolvable. I mean, it's very difficult. I mean, we couldn't get the solution because of this terms at the bottom. So they earlier studies by VTAM and so on, they didn't have this term because they were looking at no base flow or uniform base flow. So now the issue is to how to deal with it, which is not that difficult. What we can do is to take the base flow equation, differentiate it with respect to x, because we're looking at the slope of the base flow, and then you can get this equation. A little bit of maths will give you exactly the same equations as the terms in the second line in the earlier equation. This equation 10 happens to be nothing but the last line here. Now, this is all algebra, but there's a physical meaning to it. The meaning is that if you take the, if you have a solution for a disturbance of wavefront, then if there is no disturbance, that also satisfies the solution. So when there is no disturbance, the base flow should satisfy the equation which is there derived for the evolution of the slope. So that is the physical meaning of it. It's very simple in hindsight, but we had to do this thing and then figure out. So then what we have is to, we can wipe out this term on the bottom, and then you have a simple equation in terms of, for sigma dot in terms of sigmas. Now it gets even more simple. Just quickly get over this maths and get physics. So if we can do this equation, this process, not only for the slope equation, but also for the base flow equation, and do a little trick, and then we can use the, you can get the equation aij minus x dot delta ij multiplied by sigma j equals 0. This is very nice because you can then write sigma j in terms of the right eigenvector, which means everything can be written in terms of one variable. You can have all the variables will jump across a shock, but everything can be connected together with us using this right eigenvector in terms of some one quantity sigma. Now, using the definition sigma j equal to sigma times the right eigenvector, you can write the equation in terms of a very simple Riccati equation for sigma, which has just terms like sigma dot, sigma, and sigma squared. Now, this is a Riccati equation which can very easily be solved by using the transformation. If you write in terms of 1 over sigma, then it becomes a linear equation, and then you get a simple first year calculus solution. So in summary, we got slope of the flow variable in the wavefront as a simple Riccati equation. Just rewrite it in a more friendly form. This is probably the textbooks how they write the Riccati equation. So you have a linear term and a non-linear term. Now the location of the wavefront is y equal to x of t. Now we can, we may want to get rid of this time, and it's more convenient to write in terms of a distance because you're always looking at where the shock is forming when you look at a duct and so on. So we make this transformation dy by dt is x dot, and then you can rewrite this q and get a very simple equation, really incredibly simple equation for sigma in terms of the distance y. Now solution is, like I said, in first year calculus textbook, you can write a solution. This is actually a solution for a linear Euler equation, and where you can write the evolution of 1 over the slope as some, in terms of some integration factor, and the integration factor here can be e power minus of the q function, and which therefore you can write the solution sigma y in terms of the initial slope, because when you have a disturbance starting off, it has the slope as this form. Now if you look at it, there is a factor here which has this integral term. If you forget about this, all you have is sigma naught if if naught. So this is like a scaling, this is like a linear factor which just amplifies or decays the function. But then there's this nonlinear term in the denominator, which you all know, we just got an expression for it, that's all, sitting in the denominator. So, and for a compression wave, sigma naught would be less than 0, and for an expansion wave, sigma naught will be greater than 0. And just to remember that, suppose you're looking at sine wave, because acousticians like sine waves, sigma naught would be product of amplitude and frequency. That's the slope of the sine wave is omega a or something. So having got the solution, just take a look at it with the linear theory one more time. So I of y depends on base flow, and sigma y by sigma naught equal to I of y by I of naught. So this is only when linear effect is concerned, and this is very simple, and this is the solutions which are there in the linear acoustics, like Ray theory of acoustics. Now, that means the scaling is same for both compression and expansion wave, and you can work out the expression for I of y. It's very easy. For example, in a variable area duct, it is going like 1 over square root of a of y. So now we make some definitions. We look at call base flow a diverging field if I of y is a decreasing function, and base flow is a converging field if I of y is a increasing function. So this is just to keep the discussion simple. In a converging field, I would think that we can always imagine like a cone or something where a disturbance is coming through and strengthening, and we can also look at a cone which is opening out, which is diverging, where a disturbance comes, it will decay down. So based on this intuitive feeling, I call when IFY is decreasing, that's when this attenuation will happen, or decay will happen. That will be called diverging field. And when IFY is increasing, the wave will strengthen and slope will increase, and it's called converging field. This is my own definition. So looking at this expression just one more time, and we can see that the presence of the integral shows that there is a history effect of nonlinearity, which is something you would expect in a nonlinear system. There's a history effect, and the nonlinearity combines with the linear scaling and makes the process more complex compared to the classical linear acoustic ray theory. And you can see clearly that the nonlinear distortion is different for compression and expansion wave, because for expansion wave there's a minus sign which would eventually lead to the denominator becoming 0, which means the slope blowing up. Whereas for an expansion wave, this is a plus sign, so there's no question of denominator here becoming 0, leading to sigma y become infinity. And so these are some of the critical observations I want to make. And here you can see that this I of y is integration factor divided by x dot, which is the velocity of the wavefront. So we can call that I of y divided by x dot as f of y, which is with this function is more appropriate. I would explain things in terms of that. Now, when does shock form? I was telling you that I had an expression for sigma, and when the denominator disappears, then it blows up. So that's this equation which I have written, or alternately, you can, this is the equation, or you can write in terms of f as the second equation I have written, and everything is linked to the magnitude of the initial slope of the compression wave, which will go there, and expansion wave cannot form a shock. And now for comparison purposes, we will look at a classical case where you have a straight duct and shock forms in a uniform flow. Then you can integrate this, this Fy is same as F0, so you can get Ys star, which is the shock formation in a uniform flow, as 2x dot over gamma plus 1 sigma naught. This is the formula which is there in all the old gas dynamic textbooks. So now we have this expression for a general case. When you have 0 to y, f of y or f0 dy is y star. This is now giving an implicit equation for formation of shock, which can easily be worked out. Now, we look at two kinds of f of y's, where f of y is increasing or f of y is decreasing. When f of y is increasing, then it will turn out that from this we can show that f of y, if it is greater than f of 0, actually it's enough if the absolute value is greater, then ys is less than y star. This means shock formation will be early, or you would end up favoring the shock formation compared to the case when you have a straight duct with constant properties. Whereas when you have a decreasing function of f of y, then the shock formation would be delayed, or ys is greater than ys star. Now, and you can also get a condition for shock formation, that is, if you let the flow go to infinity, let's say hypothetically, even then the shock form. So you can derive this expression, which says that you should always have a compressive disturbance should always have a value greater than this simple integral written here. Only then so you have to have the sigma not exceed a critical value. Only then shock will form. Okay. On the other interesting thing, which is not much talked about, is quenching of an expansion wave, which is a tendency of an expansion wave to move towards a permanent form, and this occurs in a highly converging field. So if you have some situation where this first, I have rewritten the same expression which I had. If I have a highly converging field where this 1 over I of y tends to 0, that this first term just go to 0, then we can take a look at this second expression, and it is possible that this limit, that is the second expression, is finite. Then your expansion waves, as they approach this limit, can reach a constant strength. So this phenomenon is defined as quenching, and it should happen independent of the initial slope. Now, you can evaluate the above limit and forget these equations. What I want to say is, if I of y is faster than I of prime y, that's what the limit ends up to be, then the wave will relax. But if you have an I of y integrating factor which is going as fast as the first derivative, like function like e power x or something, then you will have quenching, because this limit will be finite. That means no matter what disturbance strength you start with, they will all reach a constant value. This has been reported by Clark some time back in the context of waves in combusting systems, and can get into a shock if I of y is lower than I of prime y. But however, we know that expansion shock is unstable and it's not stable, mechanically unstable. So just look at some examples. We look at an exponential horn, and in a converging horn, you can show that every compression wave will steepen into a shock if you use the criteria. In a diverging horn, which means this alpha is greater than 0, then shock will form if there is a initial disturbance which is greater than this simple number. So like that, you can work out for whatever cases you have. You can derive simple expression for location of shock formation. Here is the location of shock formation. And we can also see this interesting case of quenching in exponential horn. And expansion wave will always quench in a converging horn and attain this limiting disturbance strength, and it doesn't die down. So we look at the case of a CD nozzle with a base flow, and if we first look at a right-running wave in accelerating flow. So this is the plot of the f of y. So there is a critical point MC which is around 0.21, and because f of m is not a monotonic function, it will go and come down. So if you look at shock formation in this case where you have this Mach number between 0 and MC, so as f of m is increasing, ys is becoming less than the ys star, which is the classical shock formation distance in a straight duct with constant Mach number. And when m is on this side, you will have ys greater than ys star. That means the shock will take more time to evolve. This can be physically seen because when you have very low Mach numbers, you need a converging duct to converge the base flow. But as you do this, the disturbance will actually just converge and strengthen. But after some time, what will happen after this 0.21? What happens is the base flow is accelerating. So the front part of the leading edge, the front part of the wave will try to run away from the back part. So this is a physical explanation. So now that effects become more prominent, and then the shock formation distance will start increasing, or the shock formation is delayed here. And in the decelerating flow, the reverse happens, and you come from this side, from right to left, and m is greater than mc. Ys is less than ys star, and on this part, ys, the shock formation distance is greater than ys star. So I will just skip some of the things, but show some graph here. This is the evolution of a right-running compression wave. On the left, I have shown an accelerating flow, and right, I have shown a decelerating flow. You can just take a look at the numbers of the initial slope. We are having values like of sigma, like 90 to 140, and you can see that for some numbers, they are tending to relax eventually, but for some other numbers, like higher value slope, it's tending to steepen to, and eventually after some distance, it will become infinite. Now, you look at a decelerating flow, the values which are required to become shock are much smaller. That means decelerating flow has a tendency to have shock formation faster. And this is the reason you have seen that in intake, some of the missile intakes, you have problem, they very easily shocks appear and so on. Now, this is a left-running compression wave. Same kind of thing can be seen. So if the disturbance is small, it will relax and die down. When the disturbance is large, it will steepen to form a shock. Now, interesting thing is quenching. You can see that a left-running expansion wave will quench in a decelerating flow, and you attain this limiting slope, which is dependent on the stagnation speed of sound and throat geometry. And this is the graphical illustration of quenching. I'm starting with a wide variation of initial slope, starting from 1500 to 1, and the waves, all of them is, as it approaches the throat, in this left-running case, it is attaining this exactly same value. Similarly, I'm having a supersonic base flow, and all the left-running waves, it's a decelerating base flow, and all the waves, no matter what the initial slope, is converging to form a certain initial slope. I will skip some of these things and just wind up in 2 minutes, or 1 minute. We can look at, use the same approach to look at things like expansion shock formation in fluids with a negative nonlinearity. When in negative nonlinearity fluids, you have expansion shocks happening, and the compression shocks are not stable and they die down. So we have looked at this problem, and the same approach can be used to write an evolution equation. And you see this nonlinearity parameter gamma, which is defined as 1 over A, d by d rho rho A sitting here. So this means that this is controlling the sign, whether if you have, earlier we had gamma, capital gamma is small gamma plus 1 over 2. So that now if that factor changes negative, the sign here is going to change, and that's going to dictate that expansion shocks can form and not compression shocks. So same analysis can be used for looking at MHD flows. I have similarly derived the equation for evolution of the wave when there's a perfectly conducting fluid where the speed of sound is has a component from the magnetic pressure, and you can again get a simple equation for the evolution of the slope. So I conclude here by saying that studied nonlinear propagation analytically. Why analytically? Because I didn't want to do numerics. In a generalized non-uniform gas dynamic flows, and non-uniformity in the base flow affects the nonlinear process of wave steepening and relaxing. And you can see that compression wave may relax and expansion wave may quench in the classical system. Of course, reverse results in the case of negative nonlinearity. And a non-uniform flow, nonlinear distortion depends on the direction of wave propagation. Nonlinear distortion depends on whether the base flow is accelerating or decelerating, and also again it depends on subsonic or supersonic flow. And finally, I want to thank my sponsors, Indian Space Research Organization, ISRO, which funded this study. Thank you very much.
One question is right there.
Can this analysis include base flows that have shocks in them?
No, actually, we have to go till the shock, and then this analysis will break down because, this expansion of variables is valid only till the shock. And once you come to the shock, you have to use the shock condition. And then after that, you can do it if there's some other way to flow.
Thank you.